We'll just open that up and we can open up the practical integrator file from there. So just to make things clear to everyone, when you want to open a previous file, you'll be opening the OPJ file. That's the one that you want. Okay, this is taking a moment. Okay, now once we're in, what you can do is you can go into this tab over here, the practical integrator tab to the top. That's what we named it. And you can just go into this plus symbol, schematic 1, and page number 1. That's what's going to be relevant to us. Okay. So this is our circuit from yesterday. First things first, since yesterday was your first session on Orcad, are there any doubts whatsoever with regards to how the software works, any of the placements of the components or things like that? If there are any doubts, you guys can ask me right now.
Guys, anyone, any questions?
No, sir.
Okay. So Rishi, what we do is,
Yes,
once you show them these two experiments, all right, so by possibly if they have a term test that does not make them write too many assignments, my assignment would be to complete their practicals on whatever they've done till now on Orcad. So automatically they have to complete this on a different software.
Sure, sir. Okay.
Right? Yeah.
Okay, so first we'll just take a look at our integrator circuit once before we move on to differentiator. And I would want to point out one quick thing. So when I run my integrator analyses, I run the integrator simulation, you guys will notice that I am getting the required output waveform for gain without actually implementing a formula. All of you must know by now, gain is generally considered to be output voltage upon the input voltage. But I'm directly getting the correct gain without implementing any sort of output by input formula. Can someone point out why this is so in my integrator simulation?
Could you repeat the question?
Yes, so in my integrator, I have not implemented any sort of formula for output voltage upon input voltage for my gain. But I still get the correct value of gain when I go, let's say I'm just going to type in dB here. I'm going to take it into the decibel section. And you can see that I'm getting the correct value for gain at the points that I need. I'm getting 0 dB at 10 kilohertz. I'm getting 17 dB at 1 kilohertz. Why is that so without implementing any sort of formula? I should have to implement an output voltage by input voltage formula. All right. So since no one seems to have figured it out, I'll just let you guys know. Our input voltage here is 1 volt. So when we're doing our analyses,
Rishi, just one
yes,
thing.
sir?
Guys, everyone, please switch on your cameras. Everyone, please make sure that your cameras are on. Yeah, Rishi, now go ahead, please.
Yes, sir. So this is something that I myself didn't notice yesterday, but I noticed it today while working on differentiator. So I'll just point it out that yesterday when we were doing the integrator circuit, my input voltage was 1 volt. So I did not need to implement any sort of formula for my gain because I was dividing everything by 1. My output voltage by input voltage, the input voltage was 1. So I did not have to implement any sort of formula. But today in the differentiator, we'll be taking a different input voltage, which isn't 1. So we're going to have to do that. And I'm going to show you guys how to do that in a moment. So that was the answer I was looking for, but it's okay. Even I didn't notice it earlier, so I don't expect you guys to immediately pick up on that as well. Okay, so now here we have our integrator and we want to make this a differentiator. So we're going to do what I told you guys about yesterday, right at the end of the lecture. I'm going to press Control A and Control C. I'm going to copy my entire circuit. I'm going to create a new document using this button up here, or you can use Control N, whatever's convenient. There we go. And I'm going to name it Practical Differentiator. All right, so now I'm in a new circuit and I can just press Control V and I'll have this in my hand. I can move it around wherever I want and I can just left click once to paste it. Cool. We have our differentiator circuit now, and we just need to make a few edits to get it to where we want. So as Nandinee has shown, to get a practical differentiator, what we need is an input capacitor right here. So I can just click on this capacitor C3, Control C, Control V, place it right here. And let's just move it to get the wire to connect as well. And there we go. This is our differentiator. All we need to do is take this down to 0.47 nanofarads. Okay, now to take a look at the calculations behind these values, we can just take a look here. I believe this is my differentiator. Yes, it is. So these are the calculations. It's pretty standard. You have to follow the formulas. It's already been covered in the first half of the practical. So this is what we'll be using. Our capacitors will be 4.7 and 0.47 nanofarads, and our resistors will be, I'll just name them, R1, RF, and let's just name this for now. These are our values. Everything else stays pretty much the same. Your input, your DC biasing, your ROM, and your voltage source. All right. So the first thing that we're going to do is we're going to try to simulate the differentiator using a sine wave. So we're going to go into the place part menu. I'm going to type in V sine, and just going to place this here. Does anyone remember what values we'll be putting in for these four input boxes here? Can anyone recollect what we've done yesterday? Okay, I'm starting to understand why you guys didn't have any doubts in Orcad yet. No one? All right.
Yeah, that's the reason. That's the reason why assignments need to be changed to practical orientation. So this is how the world works, Rishi. It's just that you discover it when you're on the other side.
Yes, sir. All right. So the term test is going to be fun. Yeah. Guys, GPA बढ़ा लो अभी. This is your chance. कर लो Orcad. Moving on. So this is V off is going to be the V offset. It's generally considered to be the DC offset, which we do not want at all. So we're going to make that 0. VAMPL is the amplitude, which in this case, let us take to be 0.2 volts. So this is why I specifically told you guys about how I did not implement the formula in integrator, but I will have to in differentiator because I'm dividing by 0.2 volts. So I will obviously have to include the formula. Let's start with a frequency of 1 kilohertz. Let's keep it simple and we can try some others. And this is basically the AC, which we do not want. We don't want any base AC voltage. We just want the sine wave. All right. So this is our circuit setup. Okay. Kind of gave you all a hint. I was going to ask what simulation profile to use, but I think no one's prepared yet. So I'll just create a new simulation profile. I'll name this diff. Oh, there's already a profile called diff. Okay, when I was practicing. Okay, diff1, I guess. All right, so we have created a profile called diff1. Let's run this to about 100 milliseconds. I think that should be enough. And we take a step size of 0.01 milliseconds. You can choose what you want depending on your computer speed and the fineness of the output that you want. And we can just place our input, rotate that with the button R, and our output voltage terminals. Okay, so while I'm doing this, I want to show you one more thing which I did not mention yesterday. These are the voltage markers that we use when we directly want to compare a certain voltage to ground voltage, basically to 0. So for example, when I place this input voltage terminal here, this V terminal here, it directly compares the voltage to ground and shows me what I want. But let's say I want to check the voltage across, for example, this capacitor CF. What I'll be using are these voltage differential marker pins. These will allow us to sort of normally do in a laboratory setting. We can place one voltage marker here, and we can place a voltage marker to the right here. So this allows us to get differential voltage between these two terminals, and it will plot it within a single plot. So this is just to show you how that works, but it's not that relevant to us right now. We can just place this single pin right here at our VIN. Okay. So this is ready, and I think we can run our simulation now. Simulation failed because of net listing errors. Okay, so there is some issue. Just a second. So net listing error generally means that there is some issue with my input voltage. It's not showing me any error message here. Let me just take a look at. Okay, let me just close this. Maybe let me try again. Okay, so what is happening is that while I am running the simulation on diff1, it seems to be running the simulation on some other schematic of mine, which has happened in the past with Orcad. It can cause a little bit of an issue. So what I'm going to do just to be safe is I'm going to create a new project. I'm going to name it Differentiator. So these are just some issues that I have faced with Orcad that I guess you guys are also going to learn about now. The idiosyncrasies of each software are different, and this is one that I have observed with Orcad. Okay, so I've just quickly created a new project here. I've pasted my entire schematic here. LTspice, new simulation profile, diff, okay, 100 ms, 0.01 ms. I'm rushing through this because this is something that you guys have already seen me do. And I should be able to, in theory, run my simulation. And okay, yeah, it is working. And we can just take a look. So as you can see, there is no output because I forgot to put in my pins. But you can do that even after you run the simulation. I'll just put my input voltage pin and my output voltage pin. There we go. This is a bit much for us. So I'll just make this 10 milliseconds. And we have our output. I'll take this further down to 5 so you can see it a little better. Okay, so this is that at 1 kilohertz, which is what my FA is, in of 0 dB, or again, is the output voltage is pretty much equal to the input voltage. It's just that we're going from sine wave to a cos wave. Okay, now while we're here, I'll show you a couple of other things which I did not mention yesterday. What we can do is you can see that these are the two waves, the two voltages that we're measuring. You can right click on any of the voltages, and what you can do is you can double click on any of the voltages, and you can see the different things that you can plot. This is the trace menu in Orcad. So this is where, for example, you can implement the decibels function. I can just type dB before this. I can implement a cos formula, an A-tan formula. I can average the voltage, things like that. This is the place where you get those different sort of options. And apart from that, another thing that you can do is you can go into the, just a second, you can go into the view menu. You can go into the toolbars button, and there is this button called probe. You can just click the probe option, press close. And what that will do is it will give you this menu right up here. And that allows you to do a few things. First things is that it allows you to toggle cursor button. And I click on screen. It gives me this cursor through which I can actually measure my voltages rather easily. And you can see it at the bottom right here, that as I move, the X and Y values change. And there are two X and Y values being plotted because we have two voltages that are being plotted. So this is just something that I wanted to show you guys. All right. So now that we've seen how the circuit works at 1 kilohertz, we can just take a look, for example, at 10 kilohertz. And we can just plot this. Okay. So clearly at 10 kilohertz, my x-axis is going to be crowded. So I'll just make this 1 milliseconds. And I can see that. Again, I'm not getting the fine output that I want, so I'm just going to add another 0 here, take this down to 1, apply, okay, simulation, run. These processes will become second nature to you soon enough. So as of now, you can just watch me do it, and soon enough, my user will pretty much make you guys do it. Excuse me. Okay. So we have an input voltage of 0.4 peak to peak or 0.2 peak. And we can see that our output is about 1 volt, positive and negative. So that is 2 volts peak to peak. So we're getting a gain of 5 here, which I believe is our maximum gain. But what we're going to do is we're now just going to simulate it a little bit on, let's go to 11 kilohertz. And let's see if we get a gain of 5 or we get a gain of more than 5 or less than 5. Okay, so as you can see, the gain is pretty much almost the same. Okay, it's not dropped that much. But what we can do is we can, for example, make this, sorry. Yeah, I double clicked on the wrong component. So I can make this 15 kilohertz. Yeah, there we go. So now we can see that our gain has dropped to about 1.6 volts peak to peak. So it's decreased as compared to 10 kilohertz. And let's take it at 5 kilohertz and just take a look as to what this gives us. And here we're getting, okay, again, we're getting a gain of, I believe, 0.5. Okay, yeah, we're getting 1.6 volts peak to peak and 0.8 volts peak. So what we can see is that our gain is both lower ahead and behind, or higher and lower than 10 kilohertz, which is our FB. And that's what we observed in the first half of the practical, is that we get our maximum gain at the frequency of FB, which in our case is 10 kilohertz. So what we can do now is that since we've understood how the output voltage here works, we can just take this out and we can put in our VAC and we can check the frequency response. Okay, I'm setting myself up for failure here, but does anyone remember what simulation profile I have to use to get a frequency response? Guys, you just need to tell me the name of the simulation profile. I'm not even going to ask for values. Okay, right. This semester will be great for you guys. Trust me, when it comes to simulation softwares, you want to get on it as soon as possible. I made that mistake with LTspice and it's Sem 7 and I'm struggling. That's the reason Nidhi and Nandinee are teaching you all LTspice and I'm teaching on Orcad. Because I'm good with this and I made the mistake of not learning LTspice soon enough. So trust me, while you can, take the opportunity, learn it well. Anyways, so what we're going to do is we're going to go into new simulation profile again, right up here. And we're going to try it, let's just say frequency response. Okay, the name doesn't matter, but it just helps to keep things clear. Cool, we're going to go into AC suite. This is the one that we'll be using. We have our logarithmic graph setup. We have the decade counter setup instead of octave. Starting frequency, I'm going to start with 1. I'm going to go up to, so what I want to do is I'm going to go up to 100 million. You generally go to a higher level in 100 million to get the, in a differentiator, get the complete frequency response graph. So what I would do is I would naturally, normally type in 100M. But for some reason, this is giving me an issue here in Orcad. But I'll still just show you guys what I'm talking about. So this will become 0.2 V, our input voltage, and I'll press play. So as you can see, I'm getting some sort of error here, and you can specifically see that this part has been marked red. So this is how you read errors in Orcad. You'll get this sort of window, and whatever is red is generally where the error is, but not always. And we're lucky that we have just one line of errors here. I have had times in Sem 3 and 5 where my entire screen has been errors, but let's not go there. So yeah, 100 million is the issue here. So what I'm going to do is, okay, this is in the middle. Yeah, I'm going to go into edit simulation profile, and instead of 100 million, I'll just add a few zeros and I'm going to make it K. So just multiplying it by 1,000 and I'm going to run the simulation. This doesn't work, I'm going to be in a bit of a trouble. Yeah, okay, so it is working. And now what I just need to do is I need to place my output voltage probe. Okay, I've placed my output voltage probe. And now I can look at the frequency response. So what I'm going to do is, this is okay. So this is our output voltage, and now we want to see how this looks in the decibels format. So I'm just going to double click this, the voltage name here. I'm going to type in dB here. I'm going to put in the brackets, and there we go. Okay, so this is wrong. I'm getting the wrong graph here, because at 1 kilohertz, my gain is supposed to be 0 dB, and at 10 kilohertz, my gain is supposed to be much higher than 0 dB, around 15 to 20 decibels. Can someone point out as to why that is happening? I'm getting the wrong gain here for my frequency response graph. Guys, I spoke about this like 10 minutes back. Anyone?
Is it because of the input voltage that we applied?
Exactly. So I did hear what I did in the integrator. I was lazy. I just put the output voltage terminal and I expected to get the correct output here. But that worked in integrator because our input voltage was 1 volts. So I did not have to divide the output voltage by anything, because dividing by 1 doesn't matter. But here, since our output voltage is input voltage is 0.2 volts, it is causing an issue, and I do have to do a slight division. So what I'm going to do is, I'm going to go in here. Okay, and you can see this. So within the brackets, within the dB brackets, I'm going to actually divide the VU4 colon out by, I'm just going to scroll down here a little bit, by R11. So that is the first terminal of resistor 1. Let's just take a look at what the first terminal of resistor 1 is. The first terminal of resistor 1, as you can see here, it tells you the number. It tells you R11, R22. That is the input voltage. So I'm just going to divide it by VR11, and I'm going to click OK. So as you can see here, now my gain at 1 kilohertz is exactly what I want. It's 0 dB. And my gain at 10 kilohertz is much higher than that, at around 15 dB. So technically what you're supposed to get is 20 dB, because the gain is supposed to be 20 dB per decade. That's what we've designed it to be. But in a practical application, you generally find some error. I'm not sure what the error percentage was on LTspice, but here we get 15 dB per decade instead of 20 dB per decade. Now what I can do is I can just click the toggle cursor button. I can place it right here. I can place it right here. And we can see that at around, at an X, at a Y value of 1 kilohertz, we are getting an X value. Okay, this is not very clear. Hold up. It's not showing me the correct X value. I guess I have to figure out the cursor settings a little bit. My bad on that. Really sorry. But we can still just see visually that it is giving the 0 dB per 0 dB at 1 kilohertz that we want, and the gain is maximizing at 10 kilohertz. Okay, so I want to show you guys one more thing. That is how to change the scale on your axes. So if I just double click on the axes, let's say I double click on the Y axis, I can go into the Y grid button here, and I can remove this automatic button right here. So what you can see is that it's putting in one measurement at every 40 decibels. I don't want that. I want it at, let's say, 10. At every 10 decibels, I want a new measurement. So I can do that, and I can get the exact scale that I want. Pretty simple. Just wanted to show you guys as this can be useful. And yeah, so this is this. Has everyone understood what I have done here in this formula? Is this clear to everyone? Because this is something you'll be using several times over in the coming months. Any doubts as of now?
Guys, anyone any questions?
No.
Please ask.
No, sir.
All right. Okay then.
Rishi, you can
So,
proceed. Yeah.
yes, sir. Okay, so we're done with simulating the sine wave on the differentiator, and we got the cos wave that we so desired. We're going to just try out another few things now, which is the square wave and the triangular wave. So I'm actually going to do the triangular wave first, which is V pulse. Just going to place this here. Again, our V1 will be 0.1 V. Our V2 V2 will be minus 0.1 V as plus 1 V minus 1 V. We do not want any sort of delay or whatever. TD is delay. T rise is the rise time. So let's make the rise time, let's say 1 millisecond for now. We can always change that. Let's also make the fall time 1 millisecond because we want it to be symmetric. Sorry, 1n. The pulse width will be nothing. The pulse width will be nothing because it's a triangular wave. We don't want the wave to sort of stay at that V1 or minus V1 at all. We just want it to reach the V1 and then immediately fall back down to V2. So that's why the pulse width is going to be 0. I made the mistake of giving it a positive value yesterday, but I won't make that today. And the period will have to be twice of your rise time or your fall time, because the amount of time it rises, the amount of time it falls, the total time will be your time period. Since we have 2n here, what we're going to be doing is we're running this at 500 hertz as of now, 500 hertz. So we're going to go and we're going to make a new simulation profile. And what we're going to do is we're going to inherit our settings from the differential simulation profile, from the diff simulation profile, not the frequency response simulation profile. We're going to do this and we're just going to name this triangular. All right, there we go. Okay, these settings are pretty much all right, but since we're running for 500 hertz, I believe I should make this 100 milliseconds. There we go, torturing my laptop again. I'll make this 0.1 milliseconds instead of 0.01. Apply, okay. And we can just put in our voltage terminals, voltage probes here, and we can see what we get. Right. Okay, so there we go. I'll just change the timing here a little bit. Let's make this 10 milliseconds. There we go. Perfect. So we can see here pretty clearly that we have our input triangular waveform. And the triangular waveform is rather perfect because we're running it at a lower frequency. So we're getting the ideal differentiator that we want. I mean, I shouldn't say ideal, but we're getting a perfect simulation. And we're getting a square waveform here. Okay, now the square is, so to speak, not completely perfect because it takes us a small amount of time to charge up. But for example, if we take it back to 100 milliseconds, we can see that the square looks relatively perfect, but that's just a Jugadu method. So anyways, let's take it back down and we see the correct output that we want. Now, one thing is that we are getting a very small gain. So for a 100 millivolt peak or a 0.1 volt peak, which is getting a 0.3 volt output. And that is pretty much in line with what we've seen. Since we're below since we're below 1 kilohertz, since we're below our FA value, our gain will be less than 1 or it will be less than 0 dB. That is negative. So we're seeing that pretty much correctly. And now what we'll do is let's increase the frequency by a significant amount. I believe we ran this at 500 hertz. Okay, so we can run this at 0.5 milliseconds. 0.5 milliseconds and 1 millisecond. This should be able to give us our output at 1 kilohertz. Yeah, and I'll just make this 1 millisecond. Okay, too much. This. Okay, there we go. So now we're getting hold on, let me just check. Yeah, 1 millisecond. Okay. Right. So now we're getting pretty close to the the gain of 1 or 0 dB that we were talking about, but I have observed that in the practical world, we do not get the exact value, at least with a square wave. Sir, I'm not quite sure as to the reason why we don't get the perfect 1 gain in a square wave, but this is what we get. So I'm not quite sure as to the reason, but I'm aware that this is the case, at least with the square and triangular waveforms.
Yeah. So I'll take this up possibly when I explain them the theory of it.
Sure, sir. Okay, so we see this, and we're just going to take a look at it at 10 kilohertz now. We're just going to take a look at 10 kilohertz once, and then we quickly move on to the the square waveform. So all of this will be just divided by 10. This can be made 0.1 milliseconds. You can run this. Okay, this is going to be a very filled graph. And it's taking some time as well. It is. Divide this, 1 millisecond. There we go. So what we can notice here is that despite running a triangular wave as our input, instead of getting a square wave as our output, what we're getting is a sine wave, which is absolutely not what we want. But what happens is that since we're running it at such a high frequency, Orcad, or I mean, basically the Opamp is not able to handle such quick changes. Sorry, I think I put in the wrong 500. Oh, I put in microvolts, so I put in millivolts. There we go. So we can see that our gain has clearly increased at 10, and we are getting approximately a gain of 4.5 instead of 5. It's not the ideal value we wanted. But that is because before the op-amp reaches the output voltage that it wants to, switching has already occurred, and we're moving back down to the negative end of the spectrum. Okay, so I hope everyone has understood the triangular waveform. Are there any doubts with regards to this? Okay, I assume there are no doubts.
Can you just explain the part? Yeah, could you just explain the part where it, why we're getting a sine wave instead of a square?
Yeah, okay. So in simple terms, we can just take a look at this. I'll just take a look at the output once. And I'll make this 1 millisecond. So backslash. So what is happening is that since we are at such a high frequency, we're at a frequency of 10 kilohertz, which is arguably extremely high. What happens is that our op-amp is not quick enough. It does not have enough of a slew rate to be able to react to such fast changes. The op-amp and the capacitor both. The capacitor takes some time to charge up, and the op-amp itself takes some time to react to an input voltage change. And what is happening is that the input voltage is changing so quickly at 10 kilohertz. That's basically 10,000 times per second. That by the time the op-amp, that before the op-amp even reaches the value that it wants to reach, that is 0.5 volts, the input voltage has already moved to its negative value, that is minus 0.1 volts. So that by then,
it doesn't have time to stay on the constant, to stay at a constant value. It just comes back down because
exactly, there is no time for it to even reach the peak value, let alone stay at it for a certain duration. So it just moves back down immediately. Ideally, what we would want is we would want a square wave here, which goes straight up, straight down, straight up, straight down. Oh yes, wait, I can just make a rectangle here. Perfect. Yeah, ideally we would want something like this. But what happens is that this is the real world and values can't change instantaneously, at least at the output. So that's why we generally tend to use as good of an op-amp as we can. So that is the issue that we have here. Does that clear the doubt?
Yeah, it does.
Okay. So what we're going to do is we're going to delete this, and we're going to input our square waveform generator. So just take a look at this again, because some people might find this confusing if you're doing it by yourself. We go into place, LTspice component, search, excuse me, and we just go down here. Okay, it does not show me V square. I'm just going to type in VSQ. There we go. It shows me V square. Double click, and we can just place it. Since I don't have enough space here, I'll have to do a little bit of a manual placement. I'll delete this wire, place it here. I'll mirror this horizontally so that I can just have the values out here. And I'll just create a wire from here to here. All right, so our circuit is ready. Now we can just put our voltages. So I'll make my offset minus 0.1. I'll make my amplitude 0.1. A period 0.5 seconds is too high. I'll make that 1 millisecond to start with. And the rise time and fall time are pretty all right. Sorry, the rise time and fall time are pretty all right the way they are. So I can just run this. Right. Okay, this is rather full. I'll just take this down. Okay, perfect. So what we can see here is that we have our input voltage. We have our input voltage, which is a square wave this time, going from plus 0.1 volts to minus 0.1 volts. And every time there is a change that occurs when it switches from plus 0.1 to minus 0.1, there's a positive spike. And when it switches from minus 0.1 to plus 0.1, there is a negative spike. So this is exactly the output that we were looking for. I'll just zoom in a little bit for you guys to be able to see it a little more clearly. Right. So this is a sort of a zoomed in version. And what you can observe is that the switching of the square wave is not perfect. Because what you can see here is a 1 microsecond rise time and a 1 microsecond fall time. So it does take that 1 microsecond to rise and fall. That's why you're not getting the perfect square, but you do get an almost square wave. So that is at I believe this is 1000. This is at 1 kilohertz because it's a 1 millisecond wave. I can just make this, let's say 0.1 ms. We'll go relatively quickly with this because I think you've understood the concept by now. It's taking a while to simulate because it's at 100 milliseconds. I'll just take this down again to 0.5 milliseconds. Okay, a little more. That looks ugly. 1 milliseconds. Yep. Okay, there you go. So as you can see, at an extremely high frequency, what happens is that since the input voltage is switching so fast, the output voltage and the op-amp do not have enough time to properly react to the spikes, that the spikes don't even look like spikes anymore. Pretty simple. And we can just make this, let's say, 5 milliseconds, just to take a look at what it would be at somewhere around 200 hertz. Right. So at something like 200 hertz, you can see that since it's moving so slowly, the input voltage, the output voltage and the op-amp have enough time to react that you're able to get almost perfect spikes. Yeah, so this is pretty much how a differentiator works. I hope everything is clear to everyone as of now. Are there any doubts?
Perfect. This is perfect. Guys, anyone any questions? I think from my end, this was a perfect explanation. Guys, anyone any questions from your end?
Okay. Sir, I'm done from my end. I hope it was all right.
Yeah. Are you able to hear me?
Yes, sir. But your voice is very faint.
Yeah. So what I'm saying is, from my end, the particular explanation was perfect. So if the students have any particular questions, they can go ahead. But it was a perfect explanation from my end.
Okay. Thank you, sir.
Guys, anyone any questions? Please go ahead. Otherwise, then Nidhi takes over. Have all of you, so quickly a raise of hands for everyone who's understood this perfectly, because believe it or not, your exams are this simulation. Okay, so any questions, please ask. If you have a question, go ahead, please. Any questions? Okay, so I think everyone's understood this. Rishi, thank you again so much.
Thank you, sir.
Nidhi, you can take over, please.
Hi, sir. I don't mind starting immediately, but maybe after 1.5 hours, the students would like maybe a 2-minute break.
So the thing is that possibly they will start a new session at 10:10. That's the reason why I thought if you could.
Okay.
Yeah, because
Okay, yeah,
so
alright.
after this, once they have the practical sessions, they will have 2 hours free out of them. So they won't have immediately at 11:20. They can do it at their own time. So they'll have a decent break at that time.
Okay.
Guys, does that work with everyone?
Yes, sir.
Or do you all want a 2-minute break? Yeah. Okay. Yeah, Nidhi, please go ahead.
Okay. Can you all see my screen?
Yes.
Yeah.
Okay. So it's been a pretty heavy session for y'all. I know that. So we're gonna start out pretty easy with probably the easiest question you will have in this session. What is this? What's this device that I've placed on my circuit?
Here.
Pardon me?
A diode.
Yeah, exactly. It's a diode. And as most of you know, a diode has two modes of operation. Can anyone tell me that? Come on, guys. I know you know this.
Reverse bias and forward bias.
Yeah, exactly. So, to be specific, the two modes are forward conduction mode and reverse blocking mode. So, if you provide a positive voltage at the anode and a negative voltage at the cathode, that is forward conduction mode, in which the diode acts as an on switch. And if you provide a negative voltage at the anode and a positive at the cathode, then it acts as a off switch, and it's called reverse blocking mode. Now, these concepts are pretty similar in the device that we're going to study today, which is called the SCR. And you can see that the SCR and the diode are nearly identical in appearance. And this is because an SCR is a form of diode. So, an SCR, just like a diode, has an anode, it has a cathode, and then it has an extra terminal called the gate. And the gate is what we use to control the switching of this SCR. So, first of all, if you apply a positive voltage at the anode and a negative cathode, it is again the forward mode of operation. And if you provide a negative at the anode and a positive at the cathode, it is reverse. The reverse blocking mode works in exactly the same way as a diode. It simply switches the SCR off. However, in forward, you have two different modes of operation. One is forward conduction mode and one is forward blocking mode. And we're going to observe both of these here. This is going to be decided by what we provide at the gate terminal right here. It'll probably be a bit tough for you to understand without simulating. So I'm going to delete this diode. I'm going to move the SCR to the middle and we're going to build our circuit. Yeah. So what we're going to be observing first of all is the characteristics of an SCR. Also, by the way, guys, I probably didn't tell you this last time, but if you see me conjuring components out of nowhere, I didn't secretly go to Hogwarts or anything. I'm just using keyboard shortcuts. So if you press V on your keyboard, you get a voltage source. If you press R, you get a resistor, C, capacitor, D, diode. It's something that's pretty cool about LTspice, so probably use it. It makes the circuit building pretty fast. I don't know how much lag there is on screen, so I'm done constructing my circuit. Can you guys see it?
Yeah.
Okay. Now the resistor values you give here don't really matter that much except for to determine the current values. But I'm going to take 100 ohms at the gate terminal and I'm going to take 10 kilo ohms at the anode terminal. And we're just going to rename this voltage as VG, gate voltage, and this resistor as RG, gate resistor. This is RA, anode resistor, and this is DS, our input source voltage. And just like last time, I'm going to label this net as VAK. And VAK is your voltage across the SCR. We're going to use this to determine whether our SCR is on or off. It seems like there's a bit of crowding here, so let's just move this here. Okay. Now, okay, I'm just going to open my simulation command. Out of all of these, if I want to observe the instantaneous voltage, DC voltage, which of these types of simulation should I use? Any guesses?
Dot OP.
That's right, it is .op. So I'm just going to go ahead and place this .op right here. And we are going to give, for now, let's give this 0 volts and let's give this 0 volts too. We just want to see what's going to happen the moment we run our simulation. Now it's giving me an error. I think you can all read it at this point. Unknown sub-circuit called in. And then it says right at the end here, SCR. This means that it cannot find a SPICE model for our SCR. So if you right click on your SCR, you can see that there is no SPICE model loaded in here. So what we need to do is we need to load a SPICE model onto this. So at this point, this is gonna be a bit confusing. So let me know if I'm going too fast and then I'll slow it down. So what I'm going to do is I'm going to just type SCR SPICE model. And I'm going to go to ST, this website, and I'm just going to go ahead and type this. It's giving me 3 different options for SCR here, and you can select any. I'm going to select this high temperature PSpice model. Download the file, and we're going to go to the file. So as you can see, there's a little folder right here. I am just going to take that and paste it into my DLIC practicals folder. This is a PE practical, but yeah, there's already a file in here, but I'm just going to go ahead and replace it. Now, what you do is you're going to open this up and we're going to see the properties of this lib file. Do you see that this is of type lib? You're going to right click on that, go to properties and copy the file path. And you're going to go back to LTspice and you're going to click on this .op right here. Okay. And what we're going to do is we're going to paste this path and we're just going to click, type .inc before it. And lastly, we're going to paste the file name too. So I'm just going to click on this file name, copy it, and a backslash, and then paste it, and .lib. Okay. Just put this anywhere on your schematic. It doesn't really matter. Now we need to do the most important part, which is we need to actually load this into our SCR. So what I'm going to do is I'm going to go back to this lib file and I'm going to open it in Notepad, WordPad, whatever you prefer using. And I'm going to scroll down until I find this high temperature SCR PSpice library definition. And I'm going to take, okay, so they have a bunch of models listed out here. I'm just going to go ahead and take the first one. So this is the TN3050H. And I'm going to copy the model name. And I'm going to replace this SCR with that model name in LTspice. Okay. There's one last thing that we have to do. So you're going to right click on your SCR again. And you're going to click on open symbol. And the reason we do this is, if you see in Notepad right here, the order of the pins given here is AKG, anode, cathode, gate, which means anode is pin 1, cathode is pin 2, and gate is pin 3. So you're going to right click on each of these terminals one by one and make sure that they are the correct netlist order for the pin number. So A is 1, here K is 2, and G is 3. This is correct on mine because I've already done this earlier, but your gate and cathode will actually be switched when you do it, so you have to keep in mind to interchange them. And now that we're done with that, we can try running our simulation again. And you can see that it is running. It's of course giving me all of the parameters as 0 because there is no current flowing in my circuit. So I think it's time we start with this simulation. The first mode that we're going to be observing is the reverse blocking mode. So for this, sir, did you want me to cover reverse blocking mode?
No, maybe this is perfect.
Okay, so then instead I'll start with forward.
Because
Okay.
yeah, because the thing is, these guys were getting this unknown sub-circuit error in almost all their practicals that they were performing. So now they know the reason why.
Yeah, I spent hours breaking my head over this too. So
yeah. Perfect. All right.
yeah.
So I think you can go ahead with the forward blocking mode. reverse mode is asking for the amount of beams.
Okay, so let's go with forward blocking mode then first. I'm going to give 0 volts at my gate. So that means that there will also be no current applied to my gate. And on this side, we're just going to start observing our values at 2 volts. Something you're going to have to do now is you're going to have to open Excel. You don't have to do it along with me, but when you do the experiment, you're going to have to open Excel and note down your values manually so that we can plot a graph there. But for now, let's just run the simulation and see what's happening. Okay. So as you can see on the side of my screen here, it's listing out all of the voltage values and the current values in the circuit. The first value that you can see is my VAK, which is the voltage at this VAK terminal. And that is 1.983 volts. Now, why are we getting 1.983 volts? There's a simple reason for this. 1.983 is very close to our input value that we're giving as a source, which is 2 volts. So I'm just going to open this question to y'all. Why do you think that we're getting 1.983 across the SCR? Any ideas, guys? It's a tough question. It's okay if you can't answer. The reason that we're getting this almost entire voltage drop across the SCR is because our SCR is off. It's acting as an open circuit. And if there's an open circuit, your entire voltage simply just transfers to those terminals. So the reason we're getting this almost entire 2 volts drop across the SCR is because the SCR is not conducting. And you can also see that based on the current. You can't really see the value of the current here because it's in the scientific notation, but you can tell that it's a really, really low value of current. And that is because there is no current flowing in this circuit. I'm also going to show you all this for a second, which is your I across RG, if you can see. Now this is your gate current, and that is 0 because you haven't applied anything to it yet. So that will remain 0. Okay. What I'm going to do is I'm just going to go ahead and note down these values in an Excel document. So I have an Excel document here in which I'm going to just write VG equals to 0 volts and R equal to 0 amperes. And we're going to have 3 columns. We're going to have VS, VAK, and IA. So for our first value, our VS is 2 volts. AK, you don't really need to manually write them down. You can just select the value here, Control C and Control V into your Excel document. And similarly with IA, remember that your IA is your I across RA. Once I place this notation into Excel, you can see that it automatically converts it to decimals, and this is a pretty low value of current, like I mentioned earlier. Okay, we're just going to go ahead and now measure these values up to 10 volts. I'm just going to measure one more value for y'all. I have run this simulation before, so I will copy the rest of my readings from there because it's a very tedious process and we're kind of short on time today. Oh, excuse me for a second, guys. Okay. So I'm just going to open my other Excel document. Just a second. Sorry for that. So I'm gonna open my Excel doc and take down these values that I've noted till 100 volts. And as you can see in all of these, there is a very slight increase in current, and the voltage drop also remains approximately the same as the source voltage throughout. So now I'm just going to show you the graph that we're supposed to have for this. As you can see in these SCR characteristics, what we're observing first is this little blue line on the positive side very close to the x-axis, and that is our forward leakage current. So this is the current that we observe in our reverse blocking mode, and that is what we are observing.
Nidhi,
Now,
forward blocking mode.
oh, I'm so sorry, forward blocking mode, yeah. Anyway, but as you can see, there is a point here called VBO where it is breaking down, and we are going to find out what that voltage is by simply looking at our data sheet. Even until last year, I found data sheets pretty daunting to look at. It's quite scary to see so much information put into like one document and you're just overwhelmed by all of it. But it's really not that hard as long as you just read what you want. So as you can see, this parameter is what we want. That is the voltage at which we're breaking down, and you can see that so until 1200 volts it operates properly. That's a really high temperature. And I would not recommend any of you to give 1200 volts in a lab. But that is the advantage of an online setting, and we are going to give it 1200 volts here. So as you can see, it's still not broken down, and that's because they did not write that as the breakdown voltage. They simply wrote it as a voltage beyond which you should not operate the SCR. So we're going to do the obvious and increase the voltage even more. And I'm going to increase it until it reaches breakdown. So it's not reaching breakdown at 1400 either. Maybe it will reach breakdown at 1600. Yes. So you can see now your VAK is suddenly really low. It's 0.6409 volts. So I asked you about 5 minutes back what a value of VAK would mean about the SCR. Can any of you look at this value of VAK and tell me what you can infer from that about the SCR? Guys, any tries? Okay, I'll give you all the answer. This is a very, very low value of voltage and approximately a value that's pretty similar to the diode drop we used to observe across a PN junction diode too. So what we are observing is simply the voltage drop that is happening across our SCR, but the current, you can see IRA here, is 0.159 amperes, and that means that there is current flowing in your circuit. That means that your SCR is actually on and that it is conducting current. So that is what we can infer about from these two values. So you can see that somewhere between 1400 and 1600 volts, we observed breakdown. And again, that is something that you should never do in a lab, but we did it anyway.
Nidhi, so don't worry, our labs go only till 128 volts. So no chance of that happening ever.
That's true. That's fortunate. Okay, so we have finished observing these values for forward blocking mode. And what we're going to do is we're going to observe the graph for it now and see if it's similar to our graph. So what I'm going to do is I'm going to select these values and I'm going to simply go to insert, is it? Yeah. So we're going to go to insert and I'm just going to click on these recommended charts. And we're going to go for this scatter plot right here. Okay. As you can see, our line looks a bit linear right now, and it's a little hard to tell that it is similar to this line. But the moment that we add in our forward conduction mode, you're going to see how this line looks exactly like that line in the graph. So we're going to do that next. For our forward conduction mode, we take Vg equals to 7 volts. And let's see what our value of Ig turns out to be. I'm going to go and put these parameters again. And for this, we're going to start off at 10 volts. It's conduction mode, so we're going to start off at 10 volts, and we're going to see how, observe what's happening in our circuit. So I'm going to change this to 7 volts, probably bring this down. And yeah, let's run it. Okay. So what we're observing is our current, gating current is equal to minus 0.058 amperes. So let's just, wrong document. Let's add that in. That did something weird. Now I just have a question for y'all. Do y'all see how my current, gating current is a negative value? Can any of you guess why that's happening? Any guesses?
It's going in the other direction.
It's going in the other direction, but I haven't even put a probe here. So how is LTspice deciding the direction of current that it wants to take? What if I told you that resistors had polarity? Would you believe me? Or would you think, no, she's being crazy? Resistors don't have polarity. How many people agree with me? Do resistors have polarity? Anyone? Okay, everyone disagrees, and that's probably good. That means you've learned something. And yeah, you're right. Resistors don't have polarity, but in LTspice they do have polarity. So when you place a resistor in LTspice decides that one of the terminals is positive and one of the terminals is negative. You can't say it. You just run the simulation and you'll know. And the only thing we can do about this is we can rotate the component to reverse the polarity. So I'm going to, this is another amazing thing that I want to show you about LTspice. I'm just going to close the simulation window. Right. So as you can see, you have two tools here called move and drag, and they are nearly identical. Guys, just give me 1 second. Yeah, sorry about that. I was talking about the move and the drag tools. So the move tool takes your component, and as you can see, it moves only your component. And the drag tool moves it along with your wires. And the differentiation between these two tools can actually be really helpful in simulation. So if I want to rotate only my resistor, I'm just going to pick up the move tool and I'm going to click on Control R twice, and my resistor is rotated. You can also use this mirror tool right here to just flip the resistor instead. It's completely up to you how you want to do it. So now let's just run our simulation and see if our current is positive now. As you can see, I across our G is positive. And that is how you know that LTspice resistors have polarity. All right. So now we're just going to go ahead and observe the readings for this. So our VAK is now equal to 0.487 volts, and I'm not going to stop asking this question until one of you answer. So what can you infer about the SCR state based on our VAK value? Come on, guys. I literally explained this 2 minutes back. Come on, someone can try. It's all
Can you
right.
please repeat the question?
I said, what can you infer? What do you know about the SCR based on my VAK value here, 0.487?
Okay, so it is on.
Exactly, as easy as that. So the SCR you can tell is working because your voltage drop that your voltage that you've provided here is 10 volts, and that drop is not appearing across the SCR. Instead, you're just getting the internal voltage drop of the SCR, and that is how you know that your SCR is on. And then that's the other way to know your SCR is on, which is again we observe our current value, and there is current flowing in the circuit. So we're just going to note down these values in our Excel document again, and we're going to change the voltage to 20 volts. VAK value is still 0.5 something, so our SCR is still on, and our current value is this. Correct. Just like before, I'm just going to take the rest of the readings from my previous Excel document just to make life a little easier. Now we're going to add this to our chart. I don't know if you guys know how to use Excel for charts, but I'm just going to show you either way. So you click on your chart, you click on chart design, and you're going to click on select data. So as you can see, our series 1 is here. So I'm going to rename that to, we're going to call it VG equals to 0 volts. And then we're going to add a new series. We're going to call this VG equals to 7 volts, which is our forward conduction mode. For our series X values, we're simply going to select this VAK column. And for our series Y values, we'll first delete this one, and then we'll select our IA column and click OK. And now, as you can see, we've added another line here. Oh, I accidentally canceled it. Just a second, I'll do that again. Okay, as you can see, now we have two lines in our chart. I've kept these a different color deliberately so we can observe the different modes, but our orange is forward conduction mode and blue is forward blocking mode. We're going to go back to this Word document now, and we're going to observe our graph. And can you guys see that it is actually looking similar now? It's not looking the same. It's not looking the same because we have to take lots of readings to make it look the same. But do you see how this line right here is our forward conduction mode, and we're observing that, and this line right here is our leakage current in the forward blocking mode, and we're also observing that in our graph. Now, actually, if you plot the reverse blocking mode too, then it will look exactly like the graph I showed you in the Word document in the third quadrant too. So yeah, anyone, any doubts? Maybe you cannot see the graphs looking similar or something. Just let me know. Any doubts, guys?
No doubts.
Okay, that's really nice to hear. Mayur saw it's already 10:10, so should I cover the rectifier right now or maybe some other day?
No. I think we can close it at this point. It was beyond brilliant.
Pardon me, sir, I couldn't really understand what you said.
Yeah, can you hear me now?
Yeah.
Yeah, what I said was that this explanation was beyond brilliant.
Oh, thank you.
Yeah, guys, I don't know if you'll anticipate what she's done, but possibly Rishi and Nandinee would be able to make sense of what she's just shown y'all. You'll try this at your end. All right, try this at your end. Do this for triac. All right, do the same exact thing for a triac. Okay, and possibly in the next session we'll try to cover. So Nidhi, what I also wanted was if you can show them just quickly on the Excel sheet the first and third quadrant operation. If you can just show them how to plot that. Guys, what particular this thing do you all have today? What's the next lecture that you'll have at 10:10?
MPMC.
Sorry.
MPMC, sir. Vivek sir takes it.
Oh, okay. So I think we'll close it. Nidhi, we'll close it at this point. But I think they've got a fair idea. Let them try it out, and possibly they can come back to you with questions for the try.
Okay, sir. Thank you.
Yeah.
Thank you, guys.
Excellent. Nidhi, again, excellent again. Yeah. Thank you, everyone, guys. We'll drop it off and we'll pick it up in the next class.
Thank you, sir.
Yeah.
Thank you,
Thank you,
sir.
everyone. Yeah. Have a nice day, everyone.
Thank you, sir. Bye.
Yeah. Bye, Rishi. Bye, Nandini.
Bye bye, sir.